Sai Sumit, are you there? Sumit.
Yes, sir.
సుమిత్ నువ్వు క్లాస్లో ఉంటున్నావు, కొంతసేపు తర్వాత ఎగ్జిట్ అయిపోతున్నావు మధ్యలో. మళ్ళీ నోట్ చేసుకుంటున్నావు లేదా నాకు తెలియట్లేదు.
నోట్ చేసుకుంటాను సార్, మొన్న నెట్ ప్రాబ్లం వల్ల అయిపోయింది సార్.
అవన్నీ కుదరవు సాయి సుమిత్, యూ షుడ్ బి కేర్ఫుల్. నౌ లిసన్ దిస్ క్లాస్. ఓకే, గుడ్ మార్నింగ్ టు వన్ అండ్ ఆల్. నౌ in today's class we will see to calculate the fixed end moments as well as the final end moments of a continuous beam with support element. And further we will see how to draw the shear force diagram as well as bending moment diagram. Now in this class I am starting with this problem. A continuous beam is loaded as shown in the figure. During loading, the support B sinks by 10 mm, and we have to calculate the final end moments at the supports, as well as we need to draw shear force diagram and bending moment diagram. Here the values of E and I are given. So we can write down here EI is nothing but flexible rigidity. EI is nothing but 200 into 1600 into 10 power 4, which will give in terms of kilonewton mm square. I would like to write down in terms of kilonewton per meter square, sorry, kilonewton meter square. So this can be modified as 200 multiplied with 1600 into 10 power 4 by 10 power 6. It will give kilonewton meter square. So which is nothing but, so the flexible rigidity EI is nothing but 3200 kilonewton meter square. Now we will first of all calculate the rotational factors. Here this is A, B, C. Now write down rotational factors. So the rotational factors which are calculated joint B. So initially we are calculating at joint B. So RF BA is equal to, we know that minus half of KBA by sigma KBA. So minus half of KBA. KBA is nothing but, here for BA, A is fixed one, B is continuous, so that is I by L only, which is 2I by 8 by KBC. In this, you can see here support C is a roller support. That's why there will be a reduction in the stiffness, which is 3/4 of I by 4. So this is our relative, how we calculate, how we write down. So in this case, minus half of, so this value will be minus 0.28. Whereas BC minus half of KBC by sigma KBC minus half of KBC. So KBC is nothing but, we have already written, which is 3/4 of I by 4 by 2I by 8 plus 3/4 of pi by 4. 0.22. So the joint B is the one where we need to calculate the rotational factors. So the rotational factors are calculated. Now calculating fixed end moments. So we need to calculate the fixed end moments. The fixed end moments are MFAB is equal to minus WL square by 12 minus 3 into 8 square by 12, which is minus 16 kilonewton meter. MFAB is minus 16 kilonewton meter, whereas MFBA is equal to plus WL square by 12, which is plus 3 into 8 square by 12 plus 16 kilonewton meter. Minus WL by 8 minus 8 into 4 by 8 minus 4 kilonewton meter. Similarly, MFCB is plus WL by 8 plus 8 into 4 by 8 plus 4 kilonewton meter. So these are the fixed end moments due to the external loading. So due to the external loading, we have calculated the fixed end moments. Now, after calculating the fixed end moments, we require here in the question, you just go to the question, you can understand here what it is saying. The continuous beam is to be analyzed with support settlement. So when I say it is a support settlement, so just see this one, support B sinks by 10 mm. So corresponding to this, we need to calculate the support, that is the fixed end moments due to settlement of supports. Fixed end moments due to settlement of supports. So keep say heading fixed end moments due to settlement of supports. Due to settlement of supports. So just I will draw the diagram how it looks like. So it is given that first of all I will write down for AB. In case of AB, what's happening? This is your A and B. They will be considered as fixed, but it is said that B settled 10 mm. So 10 mm you convert in terms of meters, which is delta is 0.01 meter and the length is 8 meters. Now how the moment of resistance will be there? The moment of resistance will act, this will act like this. Here it will act like this. What is the direction of this value? This is anti-clockwise. So this is A, this is B, this is B dash, anti-clockwise, and we know that the value is 6 EI delta by L square. So this is also same, 6 EI delta by L square. So writing down fixed end moments MFAB is equal to, as this is anti-clockwise, our convention, sign convention is negative minus. I will simply keep it as dash m dash FAB, which is the indication of fixed end moments due to support settlement 6EI delta by L square. In the other way, if you want to remember, we have already said that compare it to left side, right side in downward direction. So delta is, so that is positive. So minus 6A delta by L square, delta will become positive. Or otherwise the original calculation will be like this. Anti-clockwise it is negative, so minus 6 into EI value. Just now we have calculated the value of EI, which is given in terms of mm4 as well as kilonewton per mm square. So that is in an overall, the unit should be kilonewtons and meters. Distance will be in meters. So 3,200. 3,200 multiplied with delta. Delta is given as 10 mm, so take it as 0.01. And L value length is 8 square. You will get m dash FAB as
minus 3, sir.
what is this value?
Minus 3.
Minus
3.
Okay. Just have a look on this. This is EI. Now go to our beam AB. In this beam AB, it is mentioned as 2I. Don't forget the moment of inertia value. So I will become 2 times. So we need to multiply with 2 here. So this is to be multiplied with 2. So you will get this one as minus 6 kilonewton meter. So C is 1, EI value is 3,200, but our value is 2 times of EI. So 2 times of 3,200, which is minus 6 kilonewton meter. M dash FBA is, this is also minus 6 EI delta by L square only, minus 6 times of 3,200 into 0.01 by 8 square minus 6 kilonewton meter. Whereas coming to BC span, so what happens for BC span? This is your span of length 4 meters, which is fixed here. So we are calculating fixed end moments due to support settlement. So this point has become like this. So now in this case, this is delta. Now what is the direction of the moment? It tries to resist like this. It tries to resist like this. And the values are, they are positive. 6 EI delta by L square. Here I is I only, L is 4 meters and delta is 0.01. And if you write down the fixed end moments, M dash FBC is plus 6 EI delta by L square plus 6 into 3,200 into 0.01 by 4 square.
12 kilonewton meter.
12.
12, sir.
Plus 12 kilonewton meter, that is M dash FBC. M dash FCB is plus 6 EI delta by L square only, which is plus 12 kilonewton meter only. The support moments, that is Okay. Now, after calculating this, we have to first of all go back to our beam. Just observe the beam. What is there? Your support C is roller support. So you have to balance that. You have to balance first. We have to first of all balance that, then only we can move further. Okay, so for that, modified fixed end moments. So we'll write down modified fixed end moments modified fixed end moments due to hinged ends. As the ends are due to hinged ends or roller ends, we have to modify the end support, the moments, whatever we got. So for this, first of all, I will write down this like this. Your support. So the supports are nothing but A, B, C. Moment, fixed end moment due to loading. Fixed end moment due to loading. So due to loading means your member is subjected to loading. So in that case, what are the moments? Minus 16. So this is nothing but a B moment. So if you see, moment is nothing but support moment AB. So here you will be having two things. One is BA, and the one is BC. And the last one is CB. So the fixed moment due to loading is written, which is at AB, the value is minus 16, which we have written WL squared by 12. So substituting the values, we got a value of minus 16, whereas here this is plus 16. All the values are in kilonewton meter. This is minus 4 and this is plus 4. I'm just writing these values from these values. Minus 16 plus 16 minus 4 plus 4. Now we will once again write down final end moment, fixed end moments due to settlement of supports. Fixed end moments due to settlement of supports. Fixed end moments due to settlement of supports. So due to settlement of supports, here we have already calculated, that is minus 6 plus 12 plus 12. So total fixed moments. In this case, just add everything. Total fixed moments, which is minus 22 plus 10 plus 8 plus 16. Just we have added, as in the case of moment distribution method also, we will first of all, in the first step, we will add the fixed end moments. In a similar manner, you add the fixed end moments due to loading as well as fixed end moments due to support settlement. Then we know that as support C is a roller support, the moment at this point will become 0. Balance support C balance C. So when you are balancing C, how you can balance? Apply opposite moment equal to that of the moment that is available. So plus 16 is available, take minus 16. When you are balancing, obviously carryover moment will be there. That carryover moment will be half of that value, and this is minus 8. Is minus 8. That's it. So now write down the moments. Modified fixed end moments. Modified fixed end moments. And the values are minus 22 plus 10, 0, 0. It's okay. Here we can stop the problem without going to Kani's method. We might have stopped our problem when the joint condition is satisfied. This is plus 10, that is 0. The joint condition is not satisfied at joint B. Now with the help considering the rotational moments, we will calculate, we will do the iterations through iterative process. We will calculate that means the moments as well as the joint will be balanced here. Now, go to the next step. We will draw the beam. Representation will be like this. This is A. C. The fixed end moments are here, minus 22 plus 10, 0, 0. And this value is and the restraints values are, this value is minus 0.28. Minus 0.28 towards RFBA, and this is minus 0.22. Minus 0.22, and this point is B. Now we know that the restraint moment at B is nothing but plus 10, 0. So this will be plus 10. In the inner circle, you mention which is the summation of the fixed end moments, plus 10 plus 0. Now, here we know that in the iterative process 1, MAB will become 0. MBA is nothing but RFBA into MFB, that is the summation of the fixed end moment, the restraint moment, plus AB sigma. So RFBA is minus 0.28 into plus 10 plus MAB is 0, MCB is 0 only here. That is 0 only. So the value is minus 2.8. So this is 0. This value is minus 2.8. Minus 2.8. Similarly, calculate MBC is RF BC MFB plus sigma MAB minus 0.22 into plus 10 plus 0 plus 0, which is minus 2.2.
Sir, sigma MCB kada.
Yeah, you just see this one. If I write down this sigma MAB or sigma is MAB plus MCB only. That is, representation will be the same. Whatever you are writing, that is sigma. If I write MBC also, I have to write down, sorry, MCB. That is also this one only, MAB plus MCB. If I write this one also, this is MAB plus MCB. Why? Because we are for B, the far ends are AB as well as CB. That's it only. Okay. Now in this case, MBC value is minus 2.2. Now this is MCB is 0 only. Why? Because it's already balanced and the rotational moments are not at all calculated. Now just as the far ends are 0, when you repeat that once again, the iteration also, you will get the same value. There is no change in the values of the MAB as well as MCB values. So you can stop your iterative process here. That's it. You can stop here and you can write down the final end moments. AB is equal to MFAB plus 2MAB plus M A. So MFAB is just go to the modified fixed end values. Don't go to the initial values. We have to consider the modified fixed ends, which is minus 22 plus 2 into 0 plus MBA minus 2.8. Then this will become minus 24.8 kilonewton meter. MBA is equal to MFBA plus MAB plus 2 MBA, and this is MFBA. Just go to this value plus 10. Plus 0 plus 2 times of minus 2.8, and the value will be plus 4.4 kilonewton meter. MBC plus 2 MBC plus MCB. MFBC is 0 only, plus 2 times of MBC minus plus MCB 0, so minus 4.4 kilonewton meter. MBC is calculated, you calculate MCB is 0 only. There is a roller support and hence MCB will become 0. So once again I am repeating the problem. Please see this. We are calculating the final moments at the supports when the continuous beam is having a support settlement. The support settlement B is given as 10 mm. A and C they don't sync. And here the moment of inertia is given as well as Young's modulus E is given in terms of kilonewton and mm. EI is nothing but 200 into 1600 into 10 power 4 kilonewton mm square. Now we want a value in terms of kilonewton meter square. That's why the mm square value is converted with kilonewton meter square. Initially, calculate the rotational factors. See, the rotational factors we already know how to calculate, which is nothing but minus half of relative stiffness of the member by relative stiffness of the joint. Here, the relative stiffness of the member for AB is I by L only. Why? Because both the ends are fixed. Whereas coming to C, there is a reduction in the stiffness due to the roller support. So that's why this will be considered 3/4 of I by L. Three-fourth of I by L. Now, what happens? We got a values like this. After the joint calculation, joint B rotational factors are calculated, go for fixed end moments. The fixed end moments are calculated. Similarly, calculate the fixed end moments due to settlement. So here, while calculating the support settlement, your AB member is 2 times of EI as moment of inertia is 2I. So here we need to multiply with 2 times of 3200. You will get fixed end moments due to support settlement for AB as well as BA. Similarly, you calculate for BC and CB. Now, as support C is a roller support, the moment at that point is 0. We should modify that first of all to proceed further. So modified fixed end moments due to hinged supports, they are calculated. And after that, we got the fixed end moments which are modified. Taking this value further, draw the diagram, represent the moments, represent the restraint moment at support B, which is the summation of fixed end moments for BA as well as BC. Now, after getting this, the iterative process is started. As it is fixed, this is 0. And coming to BA, small MBA, rotational moment, small MBA is rotational factor multiplied with the restraint moment plus summation of M. This calculate the rotational moments for BA, BC, and MCB is obviously 0. Now in this, calculating the final end moments, which is nothing but just if you observe this, it looks like our slope deflection equation, which is MFAB plus 2 times 2 EI by L into theta A plus 2 EI by L into theta B. Actually, we use it to write this equation as like this. MAB is MFAB plus 2 EI by L plus theta B. So in this is nothing but 4 EI by L into theta A. That I can write down this as 2 times of 2 EI by L into theta A, which is rotational moment MAB. So these are considered and the final end moments are calculated. You can see that the MBA as well as MBC, they are balanced. Now we can draw bending moment diagram for this. So we need to first of all draw the positive bending moment diagram as well as negative bending moment diagram over H. So while drawing the bending moment diagram, this is your support A, support B, and support C. So for support A, the positive bending moment diagram is WL square by 8. So UDL W is acting, the value is 3. So 3 into 8 square by 8, which is 24. So this value is 24 kilonewton meter. Positive bending moment. Whereas coming to this BC, WL by 4, W is 8, so the value will be 8 kilonewton meter at center, WL by 4, which is point load at center for a simple supported beam. So this is 8 kilonewton meter. Now over and above this, we need to draw our negative bending moment diagram. So the support moments are at CB 0, at BC minus 0.44, that is BA or BC support moment, that is nothing but negative only always, which is minus 0.44, the 4.4 and 24.8. So this value is 24.8. Kilonewton meter and joint. So if you observe, the hatched portion represents whatever you are hatching, that portion is representing the bending moment diagram. So shear force diagram, you people can. So this is how our bending moment diagram is drawn. And this is negative, positive, negative, positive. So this is our final bending moment diagram for the given continuous beam with support settlement.